Hi everyone, today we're going to be talking about topic 8.5, acid-base titrations. So we already discussed titrations a little bit earlier in the class, particularly in Unit 4, but a titration is essentially a method for determining unknown concentration of analyte. As a reminder, in the burette, you have our titrant, and in the Erlenmeyer flask, you have the analyte, as it already says on the slide, but I'm just re-indicating. The titrant, this one is known volume and molarity. And for our analyte, we only know the volume, but molarity is unknown. And so let's take a few different cases here. Now that we have acids and bases, you have a few different ways your titration curves can look, and you're expected to know what these should look like and how to analyze them. So let's take the case of a strong acid, strong base. Of course, our analyte is HCl, and so we should start at a low pH. As we add titrant, it's going to slowly move up until we reach right here, right to the point where the volumes of each are equal, or at least they have equal concentration. At that point, it's going to shoot up, and then it will level back off. The center of this, since it's a strong acid and a strong base, will be at a pH of 7 or neutral. And so when you reach the equivalence point, and as a reminder, the equivalence point is the same number of moles of analyte and titrant. Once they have the same number of moles in strong acid and strong base, you essentially reach the equivalence, which is literally known as the equivalence point. You essentially get to a neutral pH. And so these are quite easy. Anytime you have strong acid and strong base, your equivalence point, I'm going to call it EQ point, is pH 7, otherwise known as neutral. If you add any more base, you'll see that it becomes basic. If you don't add enough, then you're still at acidic. And so strong acid, strong base, this is a quite an easy titration. Now let's think of the case of a weak acid and a strong base. Again, in this case, our strong base is still our titrant, so strong base is titrant, and our weak acid is the analyte. So since the weak acid is our analyte, we're going to start acidic. But an important thing to note is that you start at a higher pH because it's weak. And we'll talk more about this as we move on. But the important thing to note is that compared to the strong acid component, you'll start at a little bit of a higher pH because it's a weaker acid. So as you add base to this, the most immediate thing that you'll notice is that the pH goes up a lot faster until it reaches that volume of titrant, 50, and we reach the equivalence point. It's just this time, the equivalence point is going to be a little bit higher. So if we look here, the center is right around here. If I trace a line, that's at about pH of 9. So the important thing to note here is that the equivalence point for strong base and weak acid is going to be slightly basic. It won't be neutral, so will not be neutral. And the reason why is because we're using a strong base. Right, the strong base completely dissociates, and so there's going to be a lot of OH minus in solution. The weak acid isn't going to fully dissociate, and so when you get the same number of moles, what will happen here is that your pH will essentially be higher because you have more of the OH minus actually dissolved in the solution. And so if you have here, when you reach the same number of moles, the equivalence point essentially looks like that. As you might imagine as well, the case is reversed for a strong acid plus a weak base. In that case, I'm going to write it down here. Strong acid plus weak base essentially means the equivalence point will be lower. So therefore, at an acidic pH less than 7. And so it's just the exact opposite case if you have a strong acid, weak base. Then here's just a comparison. And so here we have weak acid, strong base. On the bottom, we have strong acid, strong base. You can see here it's much more gradual, jumps up, and then goes down. Whereas for the weak acid, strong base, our increase here is much more drastic. And then, of course, you end at a higher point. So here's the center for weak acid and strong base. And right around here is a center for strong acid and strong base. So the center just moves up. We also have titrations where we have polyprotic acids. As a reminder, polyprotic. Poly means many, protic means protons. This just means more than one acidic proton. So I'll take the case of oxalic acid, which is a weak acid, and this formula is C2H2O4. We can see it has 2 acidic protons. You wouldn't necessarily be expected to know this based on the formula. I'm just telling you. What will happen here is we'll have gradual increase followed by that equivalence point. And this is essentially Ka1, right? It's the acid dissociation constant for that first proton. Then it'll increase and we'll have a second jump. And this is Ka2. And so in a polyprotic acid, you'll essentially have multiple jumps for every proton that is acidic in that molecule. So let's look at this example problem right here. We have B, which is a weak base, as we're told in the prompt. We have HCl, strong acid. This makes HB plus and Cl minus. And then we have this titration curve. You'll notice the pH here at equivalence is 6. For this particular problem, we're not too concerned with that because we're not interested in finding the pH. If we look at our question here, we're asked which of the following is the best estimate for the initial concentration of solution of the weak base. So we want this concentration at the start, right, initially. So for a problem like this, it'll be quite a simple workflow. You're going to be tempted to use a rice table, but for this particular problem with titration, you actually don't need one. And so what we need to remember is that here, right here, at the equivalence point, we have the same number of moles of acid and base, right? Because that's the definition of the equivalence point. It's the same number of moles. And so we know the concentration of HCl and we know the volume. And so we can find the number of moles of base by simply doing the concentration of HCl times the volume added. Here I should say the initial, because that's what we were given. So number of moles of base is equal to 0.100 molar times volume added, which is 0.050 liters. This is equal to 0.0050 moles of base. So now once we know the number of moles of base, all we got to do is divide by the initial volume of base, which we're given. It's just a classic titration problem. And so we're given that we have 25 milliliters of base here. So all we do is 0.0050 moles of base divided by 0.0250 liters, because that's 25 converted. And actually, there's 3 sig figs here, so I should be... actually, no, there's 3. We're good. If you do this math out, you get that the original concentration of base was 0.200 molar P. So now we just look for that answer choice, and we see that is answer choice A right there. We'll do a little bit more practice with this in class, but for now, that's all. Thanks, guys.